back in chapter 5, we diagonalized a matrix. Now we're going to focus on diagonalizing symmetric matrices. So a symmetric matrix is a matrix so that the transpose is the same as the matrix itself. Okay, so which of these matrices are actually symmetric, where the transpose would be itself? Okay, so this one, if you change the rows and the columns, this one would be symmetric. Okay, the second one, if these are symmetric, we would have to have 1, -4, 0 down the first column, which we don't. So this one's not symmetric. Okay, this one, well, you can't have, it has to be a square matrix. You can't have 5, 4, 3, 2 on the row because you can't go down the column with the same one. So that is not symmetric. 1, -3, 3, 0, no, because we need to have a -3 down that first column. ABC, we have ABC down the first column. Second row is BDE, column 2 is BDE, row 3 is CEF, and column 3 is CEF. So this one is symmetric. 0, -1, 0 is the first row, and that also is the first column. -1, 5, 8 is row 2, which is also the second column. 0, 8, -7 is row 3, which is also the third column. So this one is symmetric. Okay, so now let's look at diagonalizing the matrix. Okay, so this will be reviewing some of the things we did in chapter 5. Okay, remember to diagonalize. We want to write A as a product of a matrix P times D times P inverse. Okay, so we formed the P by getting eigenvectors for the eigenvalues for this matrix. And then the D was a diagonal matrix that had the eigenvalues down the diagonal. And then P inverse, the P had to be invertible. So we'll have a P inverse. Okay, so now let's look at the diagonalization of A. So the first step is to find the characteristic equation so that we can get the eigenvalues. Okay, so we look at A minus lambda I, which is 6 minus lambda, -2, -1, -2, 6 minus lambda, -1, -1, -1, 5 minus lambda. Okay, I want to find the determinant of that. And I want to set it to 0. That's the only way we're going to have non-zero eigenvalues, non-trivial. Okay, so I'm going to expand on row 1. I'm going to have 6 minus lambda. And then the determinant, mark out row 1 and column 1. So we'll have 6 minus lambda, 5 minus lambda, minus 1. And then plus 2, remember change the sign. And now marking that row and column out, we're going to have -2, 5 minus lambda, and then minus 1. And now minus 1, 2 plus 6 minus lambda. Okay, so now let's simplify. Okay, inside each bracket, I'm going to expand out and combine terms. Rearranging, cleaning up a little bit. I'm going to go ahead and take everything past this first product and remove the brackets and combine like terms if I can. So I'm going to have minus 10 minus 1 is minus 11, and then times the 2. So I'll have minus 22 plus 4 lambda, and then minus 8 plus lambda. I'm resisting multiplying out the first term, hoping that maybe a 6 minus lambda can be factored out of the two resulting terms that I'll have in just a second. Okay, so adding these, I have a 5 lambda and then minus 30. And notice if I take a 5 out of that, I get a lambda minus 6, which is exactly the negative of this. So I'm going to rewrite this one more time. I'm going to take out a minus 5, which will leave me with 6 minus lambda. So now I can take a 6 minus lambda out of the two resulting terms here. So I'm going to have this minus this left. So I'll go ahead and combine those. Okay, so now we have our characteristic equation. Our eigenvalues are 8, 6, and 3. Okay, so now for each eigenvalue, we need to find the eigenvector. Okay, so going back up here to this matrix, I'm going to use lambda equal to 8, and this becomes minus 2, minus 2, minus 1, minus 2, minus 2, minus 1, minus 1, minus 1, and negative 3. And then I'll row reduce. Remember, we're solving the equation, this matrix equal to 0. So think about having an augmented matrix here where that last column is 0 as we're solving this. Okay, I'm just going to go ahead and take row 3 and move it to the top and multiply it by negative 1 in the process. Okay, and now if I take twice this row and add it to the first row, I'm going to have 0, 0, 5, and then you'll see that other, what is currently row 2 will end up going to all zeros because it's the same as row 1. Okay, so we see that we have x2 as a free variable here. And we'll have that x1 is minus, okay, let me go ahead and one more step here before I do this. Let me go ahead and take row 2 and divide by 5, and then get rid of that 3 in the last column of the first row. Okay, so we have that x1 is negative x2. We have that x3 is equal to 0 and x2 is free. So my x1, x2, x3, I'm going to have negative 1 here, 1 here, and 0 here. And then that'll be times x2. So our eigenvector is negative 1, 1, 0. Okay, now let's let lambda equal to 6. So we'll have 0, okay, I'm going to take row 2, divide it by negative 2, and put it as row 1. Okay, and then I'll just put row 1 is row 2. Let me go ahead and divide it by negative 2 in the process. Okay, okay, so we've already used rows 1 and 2, so I need just row 3 now, and I'm just going to add it to the current row 1. So that'll be 0, negative 1, negative 1 half. And you'll see that row 3 will go away if I add row 2 to it. Okay, so our x vector then. x3 is our free variable now. We have that x1 is negative 1/2 x3, x2 is negative 1/2 x3, and x3 is just 3. Okay, so I'm going to choose x3 to be 2. So that would be negative 1, negative 1, and 2. Okay, and then our last eigenvector will be for lambda equal to 3. Okay, so we'll have 3, negative 2, negative 1, negative 2, 3, negative 1, negative 1, negative 1, 2. I'm going to move row 3 up to row 1 and multiply by negative 1. Now I'm going to keep row 2 where it's at, but multiply row 1 times 2 and add to it. And then our row 1, I want to multiply row 1 by the current row 1 by negative 3 and add it to the row 1 we had before and put that as the row 3. Okay, so row 2 will be 0, 1, negative 1. The last row will be all zeros. And then row 1, when I add negative 1 times row 2 to it, to get rid of that 1 position, will be 0, 1, 0, negative 1. So our vector x, we have that x1 is just x3. We have that x2 is x3. And then we have that x3 is free. Okay, so now we're ready to get started. We have eigenvectors corresponding to 8 is negative 1, 1, 0, to 6, negative 1, negative 1, 2, and to 3 is 1, 1, 1. Now, if we were diagonalizing back previously, we would just take those vectors, put them in the columns. They're going to be linearly independent. We get our vector D, our matrix D, by putting those eigenvalues in the diagonal, and we're set. In this case, I'm going to do something a little different. Notice that these vectors have a property that the previous vectors did not have. When we found the vectors, the eigenvectors for these eigenvalues, these two eigenvectors are actually orthogonal, as are these two eigenvectors or these two eigenvectors. The eigenvectors that we got as a result are going to be orthogonal to each other. Now, previously we talked about it being easier if we had a matrix that had vectors that had length 1 in them. Sometimes it made the computations easier. Okay, so when you have a set of orthogonal vectors, it's nice if you go ahead and just make them normalized as well. So go ahead and make them have length 1. So find the magnitude of each of these. This one has magnitude square root of 2. This one square root of 6. This one square root of 3. And now I'm going to write the corresponding normalized vectors for each. So this will be negative 1 over the square root of 2, 1 over the square root of 2, and 0. Negative 1 over the square root of 6, negative 1 over the square root of 6, 2 over the square root of 6, and then 1 over the square root of 3, 1 over the square root of 3, and 1 over the square root of 3. Okay, so our matrix P will have these vectors in the columns, and our matrix D. So take the corresponding eigenvalues So 8 corresponds to column 1, the 6 corresponds to column 2, the 3 corresponds to column 3. Okay, the only thing we haven't found is P inverse. Okay, it will be invertible. The columns are orthogonal. They're normalized. They have length 1. Now, because they each have length 1 and they're orthogonal and it's a square matrix, that means that P is an orthogonal matrix. And the nice thing about having an orthogonal matrix for the P is that we know that when you have an orthogonal matrix, that P inverse is just the transpose of P. So now we know what P inverse looks like. Okay, so we've now diagonalized the matrix A.